Hello everyone, my name is Ahmad Sabri. I'm from Gunadarma University, Indonesia. In this occasion, I'd like to present my short paper collaborated with my colleague, Rifki Kosasi, titled An Optimization Model for Network-Based Mobile Positioning. There are two main approaches in mobile positioning. One is satellite-based and the other is network-based. Satellite-based works by processing signals time of arrival, or TOA, from several satellites and then triangulate the discovered distances to give the mobile position. The second approach is network-based. It is established by cellular communication provider or local signals such as Wi-Fi, Bluetooth, etc. It works by utilizing network measurement report or NMR, such as signal strength, as input to prediction model, which in turn gives the estimated position of the object. Research on this subject have emerged since the beginning of 2000s, that is when the cellular phone began to be widely accessible to many people. There are three main base models. They are signal propagation model, fingerprinting, and combination of both. The type of signals range from GSM or 2G to LTE or 4G. Those methods work by signal strength or time-based. We can see that there is still room in the subject for improvement of accuracy. Given three reference points with known coordinates and an object at unknown coordinates, if the distance from each reference point to the object is known accurately, then the coordinates of the object can be discovered by triangulation principle. If, by some reasons, the reported distance is greater than the actual distance, then the triangulation creates an intersection area in which the object is located. This also holds for the case involving more than three reference points. To predict the object location within the intersection, we use an objective function to maximize the norm of the summation of vectors that begin at P and end at each reference point, which is actually the center of the cell. Briefly, in the first stage of our method, we develop the fingerprint and define the model. The second step is to implement the fingerprint and optimization model to estimate the device location. The device sends the reported cell ID and signal strength, and based on this reported cell ID and signal strength, the model retrieves the appropriate parameter from the fingerprint and maximize the previously mentioned objective function subject to intersection area created by triangulation. The result is the estimated longitude and latitude of the device and sent back to the device. The attributes in the fingerprint are cell ID, signal strength that corresponds to cell ID, the location of the center of the cell, the ground truth of location of the device, and the actual distance from the device to the center of the cell. Here we give some definitions. Let P and Q be vectors with distinct components. The similarity of vector P to vector Q is the number of components of P that matches to the component of Q. If V is a set of vectors, then vectors in V that most similar to Q are those in V that have the largest similarity to Q. The alignment vector A, P, Q is a vector such that pi matches with q ai, and ai equals 0 if pi doesn't match to any component of q. So basically ai is the index of element of q that matches to p. The matching vector mpq is a vector where mi equals 0 if ai equals 0 and mi equals 1 if ai is not equal to 0. The closeness between vector p and q with alignment vector apq is defined as kappa pq equals sigma I from 1 to nq, ai doesn't equal 0, times absolute of q ai minus pi, where ai doesn't equal 0 is a logical term whose value is 1 if true and 0 is false. So the closeness is calculated based on the absolute difference between the matching elements between the two vectors. We have vector CA, which is a vector of reported CIDs at unknown location A, arranged in decreasing order. SA, which is a vector of reported signal strength that correspond to CAI in location A. And if there is no reported CID and signal strength from the ith cell, then CAI equals S, CAI equals 0. We have the set F, that is the collection of rows in the fingerprint, which contains row vector of CIDs that are most similar to CA, denoted by CF, along with their corresponding row vectors of signal strength, denoted by SFI, where I is row number in F. The vector alignment of SA to SFI is the same as that of CA to CF, or ACACF equals ASA SFI. And for a given CF, the vector big CF provides the coordinates of location of cell CFI. Let DCIL be the column in the fingerprint and R be the set of some rows of DCIL. Then DI equals maximum of DCIL subject to R is the maximum value in DCIL subject to all rows in R. So in practical, R is subset of F. It consists of rows having SF, the closest to SA. Let ACACF be alignment vector given CAI, the ith component of CA, then delta I equals DAI denotes the maximum distance in the fingerprint that corresponds to CAI. Probably not all DI goes into the model, that is when I is not equal to AI. This is the construction of the model provided by NMR, CA, and SA, the vectors of reported CIDs and signal strengths respectively. CF, the vector in the fingerprint that most similar to CA. C capital F, the vector of location of cell CI with latitude X CFI and longitude Y CFI in radians. ASASF equals ACACF, the alignment vector. MCACF, the matching vector. Delta I, the maximum distance in the fingerprint that corresponds to CAI. And let P be the prediction location of the device with latitude XP and longitude YP in radians. PCI be vector that begins at P and ends at CI. DCIP be the distance from CI to P. Then this is the model created from this parameter. The objective function is to maximize the summation of existing PCI. That is, if mi equals 1. Subject to this triangulation, xp and yp unbounded, where the ith constraint is included if mi equals 1. Here we describe the methodology in more detail. As mentioned before, it is divided into two phases. The first phase is to create fingerprint for the target area based on these attributes. And the second phase is to deploy the mobile localization service. The device requests for its location by sending vectors CA and SA, that is reported cell IDs and reported signal strengths respectively. Then, based on these vectors, the system looks for the most similar vector of CID, the corresponding cell coordinate, and create alignment vector and matching vector. All these parameters create the specific model for the current request. The solution, that is xpyp, is then sent back to the device. Here we give an illustration on how our method works. First, the vector CA and SA are created from NMR. Then they are sent to the system, which is located in the cloud, where the fingerprint and model are planted. The function fingerprint CASA returns the most similar vector to A, that is CF, the coordinates of the cell with respect to CF, the alignment vector, and the matching vector. These return parameters then goes into the model, and the specific model of the current case is created. The solution gives the estimated location and sent back to the device. We test the method in downtown Jakarta, Indonesia, and the test results are as follows, giving minimum 1.56 meter, maximum 199.77 meter, and mean error 43.26 meter. We don't have the implementation of other methods in our testbed. So for giving some insight, here are results for other existing methods in their respective testbed. That is relative received signal strength giving 29 meters mean error, conducted in Cairo, Egypt, and Bayesian giving 52.8 meter of mean error in Tokyo, Japan. And this is the CDF of our test result. For future works, we plan to apply probabilistic approach to improve the accuracy, analyze the complexity, and implementation for indoor localization. Thank you very much for your attention.